Welcome everybody for this afternoon session of our workshop. And our speaker right now is Alexandre Stauffer from Bath. He'll be talking about random lattice triangulations.
Thank you. Is this working? Yeah, okay. So I'm going to talk about random lattice triangulation. This is a joint work with Pietro Caput and Fabio Martinelli from Rome and Alistair Sinclair from Berkeley. Let me start defining what lattice triangulations are. So we have a given point set, which are the points of the square lattice in this square from 0n to 0n. The point set's fixed, never change. And then you take a triangulation of this point set. You can take a triangulation of any point set. So this is the point set we're going to work with. And a triangulation is just a set of edges that connect points of your point set, like that one up there. And with the property that any edge intersects the point set only at the endpoints. There is never a point in the middle. And any two edges cannot intersect themselves. So if you start adding edges, you can add as many as you want. And suddenly, you get a complete picture like this, where you cannot add any other straight line edge between 2 points without violating the conditions. And it's called a triangulation because each face here is a triangle. Okay, so that's the object we are going to look at today. And some basic properties. The convex hull of a point set, which is just the boundary here, always belong to the triangulation. And, but actually, that's not the only triangulation that you can build. There are many others. For example, you can build this very simple one, where you have 1 by 1 squares with a diagonal crossing each of these squares. This is a valid triangulation. And there are really many of them. It's easy to see that there are at least exponentially many of them, since each of these, in this picture here, you can take any of these diagonals and change to the other one. So for each 1 by 1 square, you have 2 possibilities. There is at least 2 to the n square possible triangulations. And there are better bounds. The best lower bound we know is that there are at least 4.15 to the n square triangulations by Calvert Seeger from 2003. And there are at the most 6.86 to the n square triangulations. So we don't really know how many there are. We don't know how to count lattice triangulation. That's a major problem in this area, actually. So we're going to look at this kind of objects today. Let me just mention 2 very intriguing properties, just for you to get a feeling of what these objects look like. So I'm going to ask you to look at this triangulation here in the picture and try to picture, take one edge and try to picture what's the midpoint of the edge. So if you take this edge, it's not difficult to see that the midpoint is around here. But if you take the edge that go from here all the way down there, it's a bit more tricky to find where the midpoint is. But now try to see the midpoint of each edge. Try to look at the set of midpoint of the edge. So can you see it? It seems quite a complicated set, but actually it's not. So those are the midpoints of the edge. It's very regular structure. The ones here are all collinear, for example. These are all collinear. And actually, the midpoint of the edge are actually the half-integer lattice points, are points on the plane for which the coordinates are either integer or an integer plus a half. So it's easy to see that this is the case, that any edge must satisfy this condition, because the end point of the edge has integer coordinates, so the midpoint must be an integer or half-integer. But actually, if you count the total number of half-integer points that satisfy these and are not lattice points, you see that these match exactly the number of edges. So any such triangulation has the same set of midpoints. So if I just change the triangulation, the midpoints will not change. So you can try to see, if I didn't make a mistake in the picture, you'll see that each edge has the very same midpoint as before. So you could see this as, in the language of spin systems, you could look at the set of midpoint of the edge. So it's a fixed set, and assign to each midpoint an edge, and such that at the end, the total set of edges satisfy the constraints of being a triangulation, not intersect each other, not intersect any lattice point aside from its endpoints. Okay, so can see it frame this problem of lattice triangulation as in the language of spin systems, but there are some problems in looking. There are some particularities of this object. For example, there are non-local interactions between these midpoints. For example, if you look at this triangle, this is a triangle, believe me, and this edge has midpoint here, and it shares a triangle with an edge whose midpoint is up there. So you see it's far from local, the interaction, and the interaction between these midpoints actually depend on the triangulation, which is not very usual to find. And also, you have many, many choices for edges to assign to each midpoint. If you look at this midpoint here, for example, you'd have many, many, many possibilities of edges in principle to attach to this midpoint if you forget all the other edges. So you could put an edge from up here to down there, and so on and so forth. So there are of order n or more edges that you could assign to that midpoint. Okay, so that's the object I'm going to look at. And what else? Let's see. Yes, that's also a very interesting property. Even though you have triangles like this one that are very different from triangles like this one, they all have the same area. So any triangle in this picture, any triangle in any of the triangulations have area half. Actually, any triangle whose endpoints are integer and which do not contain any other integer point aside from the 3 vertices have area half. Okay, it has area half. So that's so you can see this, the triangulation of this square, that's n by n square, as a partition of the square into triangles of area half. Okay, that satisfies the lattice constraints. So let's look at this object. We're going to look at a random such lattice triangulation. So I'm going to do this via a Markov chain over the set of triangulations. You take any given triangulation like this, and I'm going to do transitions from this triangulation. The transitions will obey the following rule. First, you choose one edge from the set of internal edges. You don't choose the boundary, just a set of internal edge. You choose one uniformly at random, say that one, and then it belongs to 2 triangles, the one above, the one below here. And if the quadrilateral formed by these 2 triangles is strictly convex, then you can delete this edge and replace it by the other diagonal of the quadrilateral, and this would give you a new triangulation, different from the previous one. And you do this, say, with probability half, make it lazy, just to avoid the periodicity issues. And it's not difficult, well, it's not completely trivial to see that this chain is irreducible, but okay, let's just give another example here. If you pick that edge, you can again replace by the other diagonal. And if you pick this edge, for example, this one, if you look at the 2 triangles that contain it, does not form a strictly convex quadrilateral, so you cannot replace by the other diagonal, which would be from here to here, but it would contain this edge and violate the constraint, so we just keep the triangulation as it is. Right? So as I was saying, this chain is not completely trivial to see that it's actually irreducible, that it actually connects the whole space of lattice triangulation of the n by n box. But the way to show it is just that to verify that if you look at the longest edge of any triangulation, this edge either flips to a smaller edge, or it's actually the edge with minimum length with that midpoint. So you can always keep flipping the longest edge of a triangulation to a smaller edge until you get to a triangulation like the one with 1 by 1 squares and unidiagonal. And then you can, since this is a reversible transition, you can also build a path between any 2 triangulations. Okay, so that's the way you see irreducibility. And once you have irreducibility, it's easy to see via reversibility that this chain converts to the uniform distribution on lattice triangulation of the n by n box. Okay. Is the chain so far clear? So what we want to analyze is the mixing time of this Markov chain, just the first time that the total variation distance to stationarity is smaller than, say, a quarter. But actually, this turned out to be a rather complicated problem, so we're going to look at a small variant, a small generalization of it. We are going to introduce weights. So we're going to look at weighted lattice triangulation, where you take each lattice triangulation like this one, and we attribute a weight, which is the sum over all edges of the triangulation of the length of that edge. So we just take the sum of the length of the edge. This is going to be the weight of the triangulation. For example, here you have a triangulation whose weight is of order n square. Like each edge has either size 1 or 2, say L1 norm, so it's size 2. And you have order of n square edges here, so have n squared the weight. But you also have triangulation like this one, whose weight has order n cubed. So if you just look at it, there is one edge here whose L1 norm is of order n, and actually the next one has order n minus 1, n minus 2. So each of this column actually has order of weight n square, and you have any such column, so I have weight n cubed. And the maximum weight of a triangulation is always of order n cubed, but the triangulation of maximum weight is actually not known. So we do not know how to describe the triangulation which maximize the total weight. Okay? On the other hand, the triangulation that minimize the weight is just triangulation like this, up to flips of the diagonals, which does not change the weight. And we'll call this type of triangulations as ground state triangulation, borrowing from statistical physics nomenclature. Okay? So that's the object we are going to analyze today. And the goal is to sample a triangulation with probability lambda, which is a parameter, to the power of the sum of the weights, of the sum of the length of the edge, of the weight of the triangulation. So if lambda will always be positive, but if lambda is small, smaller than 1, you favor triangulations with low weight of this type. If lambda is bigger than 1, you favor triangulations of this type. And if lambda is equal to 1, it's exactly the case I start with, is the uniformly random lattice triangulation case. Okay? And you can simply modify the Markov chain rule using the heat bath dynamics to do the same, almost the same chain as before, so that at the time we choose an edge, and we decide whether to stay with this edge or replace by the opposite diagonal. Instead of doing this with probability half, as we were doing before, we just do the proper weight given by the Glauber dynamics or heat bath dynamics. So that the chain converges to the desired stationary distribution. Okay. So at this point, before I go to state our results, I'm going to show you this Markov chain running. So let me start picture. This is a 50 by 50 lattice triangulation. Lambda here, the device is ready to use. Good. Lambda here is of size 0.6, so it's quite small. It's smaller than 1. Favor short edge. Let's see if get out. Good. It favors short edge. So if we start the chain, you see that, well, since lambda is very small, you see that edges do not really get large at all. But if you decide to change the value of lambda, say from 0.6 to 0.9, and we speed up this, because it's a bit too slow, so we can speed up a lot. So we start seeing that some bigger edges start to form, but they also get smaller again, because lambda is bigger than 0.6, it's 0.9 now, but still it's more than 1, so it's still favoring short edge. But now, if we take the same triangulation and change lambda to 1.1, then lambda is bigger than 1, so you start favoring long edges, and long edges start to form from your picture. You see some long edge start to form here, start to form there, and when you get a long edge, say, in this direction, then the edge near to it, you start to get long and align with them. And then, again, the edges neighboring that start to get long and align with that, and they start to grow even more until suddenly they start hitting another cluster of long edges that are forming, that start to form far from the initial one, and this picture starts to get quite constrained. So the chain will start to get very, 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 the edges start to constrain one another, and this fight lasts for a very long time. And one way that we found to characterize this very slow, it suggests that the chain is very slowly mixing, because once you get to this condition, the chain, it's like a traffic jam, right? It's completely one edge constrain the other, and nobody, all of them wants to grow further, but they do not manage to because there is no space. In order for this edge to grow, this edge that's very aligned here has to shrink to reduce its size, but it doesn't like to reduce, so that it gives room for this edge to grow further. So the orientation start to collide. And one way we've found to describe this is to give color to the edge, so that edges that go from bottom right to top left in this orientation get one color, edges that go from bottom left to top right in this orientation get another color, and they're going to get a picture like this. So your n by n square gets split into red and blue pictures, red and blue edges, and the interesting thing is that the boundary of this region is always either small vertical edge or small horizontal edge. You can trace the boundary of this. And in order to transform a red edge to a blue edge, you had to get it all the way to a small edge, either vertical or horizontal or unidiagonal. So it's really, the picture gets very, very constrained. So big sets like this, big clusters like this, have to shrink all the way. So if you look at here, you have this huge blue cluster here, this huge blue guys here, and they want to connect, but they are constrained by this brave red cluster here. And in order for them to actually, convince these guys to become blue, they all have to reduce their size all the way to very tiny edge, so that they change the orientation to this way, and they manage all to change. So this is the way we found to characterize, and this it will take exponential time. Actually, if I were to let this simulation run for, say, a week, and I have done so, you'll see essentially the same picture, right? The only thing that will happen is maybe this guy here will get corrupted, it will become blue. Maybe this small strip here seems very corrupting and can become blue, but this bulk here will fight bravely. And maybe I wouldn't even live long enough to see this red guy turn into blue. So we get this problem. So let me turn off the colors again. Oops, that's another thing. And if you now, okay, that was 1.1. If I take lambda and reduce again to 0.9, starting from this very jammed configuration, then you see that easily the long edges melt down. The lambda is favoring them to be short, so they quickly melt down and gets back to that picture we were seeing before with small edge. So this suggests that when lambda is smaller than 1, the chain mixes quickly, and when lambda is bigger than 1, the chain mixes slowly. Okay. And then the question is what would be the intuition for the chain when lambda is equal to 1? And I'm not going to answer that. I'm going to set the simulation to lambda equals to 1. I'm going to minimize it, continue with the talk, and then at the end, we see what it shows. Okay. Let's see. Okay, so that's the definition of the model. Let's now go to the results. So the first results we had in this area were the following. So we show that, according to the intuition, that for lambda, any lambda bigger than 1, the mixing time of the chain and the spectral gap is at least exponentially n. And this is because of the reason I told you. There are the red guys, the blue guys, and they establish some bottleneck, or they freeze. They have configurations that are very frozen and cannot really change much. So we are able to establish a bottleneck that gives a lower bound mixing time of order e to the n. But we conjecture that the right quantity is actually e to the n cube. Right? Remember that n cube is the weight of the triangulation with largest weight, and we expect that that should dominate the mixing time. But this is still an open problem. And on the other hand, if lambda is smaller than 1, we expect it to mix quickly. And we're able to show that for lambda is small enough, where small enough here means smaller than 1/8, the mixing time is of order n cube. Right? And this we show this with a proof via path coupling with a suitable metric. And we also managed to establish in the same regime that we have decay of correlations, which means that regions that are far away from the square kind of evolve independently. And we are able to show this via a Pius argument. So it's, if you are used to work on this area, you can see that Pius argument usually do not go all the way to the critical value. So you have to work more if you want to get answers for all lambda smaller than 1. And it's easy to see there is a lower bound for the mixing time because the diameter of your state space is of order n cube. So if you look at a triangulation that has weight n cube, you have to flip, to change, to perform n cube transitions of your Markov chain to get, for example, all the way to the smallest weight triangulation. Okay, so you have that the mixing time of order n cube here is tied up to constants. Okay, so any questions? Yeah.
How large are frozen regions in the first term?
So I didn't hear.
The frozen regions in the proof of the first term, how large are they?
Yes. So in our case, what we look at was, I think I don't have a picture of this, but you look at each column, and you look at the maximum weight of each column, where you alternate columns in red and blue, red and blue, red and blue, and then this gives you the bottleneck because each of these columns are, do not allow the other column to, they cannot interact unless they change colors. So you can analyze the chain and get a bottleneck that's exponential in n.
In real life, do you typically expect to see linear size regions?
In real life, yes. I didn't live long enough to see what real life actually is, but I would guess yes. Yes. Any other question? Mm-hmm. Mm-hmm. Yes, we use a Pius argument to just look if you have, given that you have any triangulation on, say, the left side, and you want to know what the triangulation looks like at the right side, what we show. Yes, yes. We show that you can find a path from the top border to the bottom boundary of, say, 1 by 1 squares with diagonal in the middle. And this path, once you can find this path with high probability exponentially large going to 1 with the distance from the region you are conditioning on and the region you are sampling from. And once you get this path, there is the Markovian property. So you can couple two triangulations. Once you find a path from top to bottom, the same path in both triangulations, you can couple the right part of the path so that they match up completely.
When
okay? But we can talk, but don't worry, that will be something more. Any other question? Okay. So the goal is to try to analyze the case of all lambda smaller than 1. So we have the analysis for small lambda that goes only up to lambda smaller than 1/8. But how can we extend, how can we analyze the case of all lambda smaller than 1? There are some challenges to that. The first one is if I condition on a triangulation, have this edge, say a long edge here. So it's clear that first it changes the distribution of edges on this side. First because that an edge with midpoint far away, say midpoint here, there could be, so this is not the total picture of your point set. There are more points in this area. So it could be that you could want to put an edge that's long, but some edge that you could put, if you are not conditioned on the existence of this edge, you cannot put since they will cause a constraint. So we already have some limitations, even some faraway limitations, just because some faraway impact of the condition on this edge, just because of that. But also, even if you don't have long edges, you could still propagate this dependence because this edge by itself kinds of impacts heavily the edges whose midpoint is inside this contour. But this could, the presence of this big edge could force, for example, this edge to show up, which could then force this edge to show up, and this bunch of smallish edge could propagate until it affects something far away. So the region affected by an edge can grow just by stacking edges in the same orientation going all the way to the right. So there is one problem that you have to cope with. Another two problems is it's natural to believe that if I'm conditioned on one edge being very, very small, say the smallest edge I can put within that midpoint, it's natural to believe that given this conditioning, other edges will be more likely to be small, that having some smaller edges allow you to get smaller edge and to have some positive correlation. It's very natural to believe if it were not wrong. So first, don't bother about this. First, for example, there is a violation of a natural partial order. If you take two triangulations and say that one is smaller than the other, if for each given midpoint, the edge in one triangulation with that midpoint is smaller or equal to the edge in the other triangulation with that midpoint, it's a natural partial order. And here is an example of two triangulations that differ only on the green edge here. This one is smaller than this one. But if you apply your dynamics here, you can flip this edge here, and it would increase. While here, you cannot flip it. It's not in a strictly convex quadrilateral. So by applying a flip operation to this edge, you simply create an edge here that's larger than here, violating this simple partial order. So at least the simplest partial order I could think of is not preserved under the Markov chain. Another problem is there is also violation of the FKG inequality, which is given by this example here. So suppose you are looking at the triangulation given the presence of these three edges. And I'm going to give you two examples, so here and there. So there are these three edges are present. The black edges are all present in both. And then the edge with this midpoint can either be this one or this one. But this one is the longest one, this one is the smallest one. And the interesting thing is that if you condition on the green edge being the longest one, then you favor this edge to be the smallest it can be. Right? Because if you condition the green edge being there, you force the red edge there is no other option for the red edge, while if you condition the green edge being small, then the red edge can be either a straight line or can be this longish line here. So here, funny enough, by having a small edge, by setting the green one to be the smallest edge, you decrease the probabilities that this edge is the smallest you can get. Okay? So there is all this bad news. So what did we manage to do to try to analyze this system all the way to lambda smaller than 1? So first we look at not the n by n triangulation, but we look at the region n by k, where you can think of k here as being independent of n, just some constant independent of n. So let's look at triangulations of the n by k. And in this case, we can show that for all lambda is smaller than 1, the mixing time is of order n squared. Remember that the n by n case, the mixing time was of order n cubed, just because essentially the maximum weight triangulation has order n cubed. In an n by k, the maximum weight triangulation has order n squared. So the mixing time here is actually tied up to constants. And the constants, of course, may depend on your k. Okay? So that's how we can show that. And the proof goes, if I use the nomenclature, goes via the bisection method on the log Sobolev constant. I'm going to just give you some highlights of the ingredients we need to show this. So what's the idea? The idea is the following. Suppose you split your n by k region into 3 blocks. So the left block with L here, the right block, and some middle block here in the center. And suppose you are given some edge. So you are given the edges on the left, the edges whose midpoints are on the right, but you are not given the edge whose midpoints are in this middle block. Okay? So there are some edges that go from the left to the center. The midpoint is here on the left, but they may stick in the central blocks. So if I were to tell you that these edges do not stick in too much, they stick the most, say, log n, and this middle area here is much larger than log n. You can think it's probably some power of log n, some log n to the 10, or your favorite power of log n. Then this sticking in parts do not reach the other ones that are sticking in from the right. So we have a region here that's free from edge. And the probability that in this region that's free from edge, you find a crossing from top to bottom of a straight line sequence of size 1 edge is going to be very big. This is a key part of the argument. Suppose you knew that this is the case, that you can put this top to bottom crossing with very large probability going to 1 exponentially fast with m, where m is the size of this free region, the region free of sticking edge. Then, if you were to get that, so what you can show is the following, that given 2 configurations, 2 triangulations of the n by k box, for which you fix the edges that are on the left, you are given the edge on the left for sigma, the configuration sigma and eta, so this is sigma L, eta L, so the parts that are to the left. These are given to you, and suppose it satisfies this, so it doesn't go too much inside. Then you can couple the remaining part, the part of sigma and eta in the right part, so that the probability that they are different in the right part is at most exponentially small in m. So the idea is that you can find this path from top to bottom in both triangulations, in both configurations, sigma and eta, with high probability. You find it here, and once you find this, to the right of this path, you can couple them completely so that they match up to the right. Right? So with this, you can look at the following dynamics. You can take 2 triangulations, sigma and eta. You fix the configuration to the left. Suppose it all satisfies this, so you fix the configuration to the left. And given the configuration to the left, you sample the configuration in the middle and in the right with equilibrium, with stationary distribution given the left part. And you do this for both triangulation sigma and eta. And we know that since you find this top to bottom crossing with high probability, after one step, you are very likely to match up the configuration sigma and eta in the right part. And then you do the opposite. You fix the right part, and you sample the middle plus the left, also with stationary distribution given the right part. So, and once you have matched up the right part, one more step of update to the left, you manage to match up completely, because the right part has already matched up, so they have the same distribution condition on the right part. Okay? So that's a simple dynamic. You can show that these dynamics mix very quickly given these two ingredients. And then once you have this, you just need to analyze the chain in half of the space. So not half, but the chain, half of the space with some sticking edges coming from the side. Okay, so we just iterate this procedure where you look at a space of order, a rectangle of order more or less n over 2 by k with some possible sticking edge that are not big enough. And you again take this part, split it into 3, and repeat this argument. And you can keep doing this until you get to a small enough scale where you can get a not so rough bound via path coupling. The bound is not already not very trivial to get, but it works out, and we are able to plug this and show the mixing time of order n squared. So that's a very rough sketch of the proof of the mixing time. I just want to give you the ingredients that we use to show essentially these two steps. Okay? So that comes from one key ingredient in our proof. Okay, let me before just quickly tell you that the previous result we had for lambda bigger than 1, already in the previous paper we could give a better bound if we look at an n by k system instead of an n by n, and this bound we managed to get exponential in n squared. So at least for the case n by k, we have the tight bound for both lambda, all lambda bigger than 1 and all lambda is more than 1. Okay. So let me now give you the ingredient we use to prove these two results, these two key steps. So the key ingredient is a Lyapunov function on triangulations. So let me give you an idea of what this Lyapunov function is. So sigma is any triangulation. Let's call sigma prime the triangulation we obtain after one step of a Markov chain from sigma, and let sigma bar be the ground state triangulation. So the triangulation with minimal weight, but this is not necessarily the triangulations of 1 by 1 square with unit diagonal, because I'm working on a case where I can add some constraint edge, some edges like the red ones, like this and this one, that are constrained to be present in your triangulation. So I'm sampling a triangulation given the constraint edge. And the main reason I need this, for example, is when I'm doing this recursion that I mentioned in the previous slide, I told you that when going to the smaller n by 2 over by k scale, I have some edges sticking in from the right, so I have to be able to cope with some fixed constraint edge that cannot be flipped. So these red edges are always present. So given any set of constraint edge, this red edge, and if I take one edge, E, here, that is in ground state, so this edge is the smallest edge that can have midpoint here. So see, this edge is constrained by the red edge, but without the red edge, its smaller version would be this. But since the red edge is there, the smallest possible edge with that midpoint is this one. So given this edge does not need to belong to your triangulation sigma. What you do is you look at all edges, you look at all edges in your triangulation sigma that cross this green edge here, and then your Lyapunov function is just given the constraint edge and the ground state edge, just the sum over all edges that cross the green edge of this parameter alpha to the side of the edge where alpha is bigger than 1. I don't expect you to understand the Lyapunov function. I barely understand it myself. But also, especially because this is just a simplified version. This is not even the Lyapunov function. The Lyapunov function is a bit harder to describe. But do you have any questions? Yeah, more or less. Yeah, more or less. But actually, the way any alpha is smaller than 1, I mean, I didn't really care for optimizing alpha, but any alpha satisfying these two holds, but there are some simplifications that if you choose alpha properly, just the calculations are better. But this is a good flavor of what the Lyapunov function should be. You look at all edges that cross your target green edge, and you sum alpha to the length of that edge. Alpha is bigger than 1. So if you have long edges crossing this edge, the Lyapunov function is large. If you have small edges crossing it, the Lyapunov function is small. And the smallest you can get is if the green edge is actually present in your triangulation sigma. Because if the green edge is there, no other edge will cross the green edge, just the green edge itself. So the smallest you could get is alpha to the size of the ground state of that edge. Okay? So that's a Lyapunov function. We have a bunch of geometric properties of this that will show that it's a Lyapunov function. I'm not going to go through them here. Let me just tell you the consequence of the Lyapunov function. So first, it is a Lyapunov function, so that's a theorem. We show that if once given the constraint and given any constraint and given any ground state edge, for all triangulations for which the Lyapunov function is bigger than some constant times the Lyapunov function of the ground state's triangulation given the constraints, then we have that the expected value after one flip of the Markov chain decrease in expectation. So that means that if you look at this Lyapunov function, when it gets above, so the ground state triangulation has the minimum value for the Lyapunov function. When it gets a bit above this minimum value, it has a drift to go down. So it's a super martingale up above this value. So it shows you that this Lyapunov function tends to have small values. So with this, you can actually control the size of the edge. And let me give you some consequence. Before giving the consequence, let me tell you that the Lyapunov function actually works in almost full generality. It also works for triangulations of n by n square, not only the n by k. It works for any set of constraints, any edge, ground state edge you pick. You can put as many constraints as you want. It always works in this way. Okay, so it's quite a key ingredient in our proof that it has all this generality. So let me just give you quickly the consequence. For example, we can easily imply, the Lyapunov function easily imply that the size of the edges are going to be small. For example, it shows that given any set of constraints, the probability that an edge with a given midpoint x has its minimum value given the constraints is uniformly bounded away from 0. So this immediately shows you that in that middle region, that in the picture with the 3 areas, in that middle region where there was no edge sticking, the probability that you put a top-to-bottom crossing is just exponential in k, in the height, because at each of these 1 by 0 length 1 edge that forms the top-to-bottom crossing, you have a probability uniformly bounded away from 0 to put it there. So it immediately gives you that you can put the top-to-bottom crossing with constant probability depending only on k. Also, it gives you an exponential tail for the size of the edge to deviate from its minimum value by z. You give some decay that decays exponentially in z, at least, for any constraint. And also give that the largest edge you have in your triangulation is at most the minimum value of the edge, the ground state value, plus log n. So it immediately gives that all those sticking in edges have size at the most log n. Okay. Another thing that to get that if you don't force, if you're not picky with constraint, if you think about triangulation without any constraint, so just the n by k or n by n region, then we get that for any midpoint, the tail of the length of the edge with that midpoint actually decays even stronger than only exponentially. So for n by k, we can get Gaussian tails. And for n by n, we can get at least exponential z log z. There is an extra log that gives. So it's even stronger than exponential if you don't condition on any constraint. And finally, another thing I want to show that this is not a consequence, direct consequence of the Lyapunov function itself, but in the proof of the Lyapunov function, we have this interesting geometric property that it's also used in our proof of the mixing time, that if you take any two triangulations, sigma and eta, and you want, for example, to transform one into the other with a sequence of edge flips, for example, in case you want to establish canonical path kind of argument for the base of the recursion, then we can show that given any constraint, the number of edges that you need to flip in order to transform the edge with midpoint x of sigma equal to the edge of midpoint x in eta, it depends only on the difference between the size of the edge and its ground state. It doesn't depend on the size of the edge itself. The edge can be very, very, very big, but if its ground state is just a constant smaller than that, the number of edges you need to flip is just some constant that would not depend on the actual value of the edge, just the difference to its ground state. So this is very, very important, and we use it in the proof of the mixing time and in the Lyapunov function. So let me get to the, okay, I'm concluding now. So let me get to the open problems. So first open problem, if lambda is smaller than 1, for the case of the n by n, is of course to establish the mixing time of order n cubed for all lambda is smaller than 1. Another thing is to establish the existence of local limits, the convergence of to establish that the infinite volume process exists. All of this is not known even for all lambda smaller than 1, but it is known for lambda for the n by k region. So you don't know this only for n by n. So that's the open problem in the regime of lambda smaller than 1. And for lambda bigger than 1, and also n by n triangulations to establish that the mixing time is of order n cubed, exponential in n cubed. And finally, say anything about lambda equals to 1. It's all open. So I'll conclude here. Thank you.